So hi, everyone. Welcome to the talk. NoSQL developer perspective, covering basic data modeling. My name is Shtub, and I'm head of training at ScyllaDB. Throughout the talk today, I'd like it to be as interactive as possible. It's live, it's not pre-recorded. So yeah, feel free to ask questions on the chat window. I'm looking at it every once in a while. Also tell me if I'm going too fast or too slow. Yeah, let's make it interactive. So as I've said, I'm head of training at ScyllaDB. I'm based in Israel. My background is as a software engineer. Before I get started, two very useful resources that I highly recommend. One is ScyllaDB University. You can see it here. It's at university.scylladb.com, and it's our learning and training resource center. It has quite a lot of material related to ScyllaDB and NoSQL in general. Different lessons covering many topics, including data modeling that we're going to see today. And it includes videos, slides, hands-on labs. You can access it at this address. All you have to do is register for a free user. All the material is available to you. It's self-paced, which means that it's on demand. You can just take a lesson or a course whenever you have some free time. So I highly recommend checking that out. Another useful resource is our documentation. That's docs.scylladb.com. And there you have more in-depth procedures, manuals, and other stuff like that. Yeah, please mute yourself. Thank you. Okay, another comment is that all the slides that you're seeing today will be available to you. I will also share some links with you, so I will send you an email probably tomorrow, so you don't have to worry about, I don't know, writing things down or making photos of the slides. I'll send them over to you. Okay, I see there's first question. Is NoSQL a valid alternative to SQL as a transactional data store for a web app supporting inserts, updates, and deletes at the individual record level? So yeah, the answer is it depends. It really depends on your use case. And I'll try to cover that later on in the talk. If I don't, then please remind me. ScyllaDB and NoSQL in general have their sweet spot, so they're not valid for any use case. And if you have a very small application, it might be better to use SQL. So I'll talk about that as well. Okay, an event we're having. So we're having a more in-depth training event in about 2 weeks, 24th of September. It's called ScyllaDB University Live. I'll share the link to that with you. It's online, it's also free. And if you want to learn more about NoSQL, you can register for that as well. Okay, so the agenda for today is I will start with an overview and architecture, then I will dive into basic data modeling. And to understand the basic data modeling, we need to understand the architecture and how the database works also under the hood. I will cover partitions and keys, and then I would like to show you a hands-on lab where we will see some basic concepts of data modeling in practice. And that's quite a lot of material, so if I have enough time, I'll also talk about drivers and how to use them. Yeah, I see that quite a few more people joined, so I will just say that I'd like to make this talk as interactive as possible. So feel free to ask questions in the chat window or tell me if I'm going too fast or too slow. So I'm going to get started with an overview and an architecture. I'm going to use ScyllaDB as an example. However, the concepts that I'm covering are relevant for many other NoSQL databases, including Apache Cassandra, which is one of the leading databases, as well as Amazon DynamoDB and some other databases. So ScyllaDB is used as an example, but the concepts are relevant for many other distributed, high availability NoSQL databases. Okay, so some of the attributes of ScyllaDB, I just said that high availability. High availability means that the database is built in a way to remain available and be able to serve requests, even if if there's a network failure or a hardware failure, or even if an entire data center goes down, data is replicated. There's no single point of failure, and that allows the database to provide high availability. Okay, so it's a distributed database. Data is replicated. Highly scalable, that means that, again, the data is replicated and distributed across many nodes. It can be several nodes, hundreds of nodes running on different data centers, and the user can simply add or remove nodes as needed. Say we're talking about an e-commerce website that's using ScyllaDB, and they know that Black Friday is coming up. A few days in advance, they can simply add more nodes without any downtime. That way, they will be able to serve more requests. And maybe after Black Friday, they can decommission those nodes and play around with the scalability. Performance, so we're talking about, a very high performance. There's an example I'm going to link to showing 1 million operations per second. And we're talking about single-digit millisecond latency. So very high performance. Low maintenance means that the database has auto-tuning capabilities. And ScyllaDB is a drop-in replacement for Apache Cassandra and DynamoDB. And that means that if you're using an application that has that's using basically Apache Cassandra or DynamoDB as the underlying data store, you can simply change it to use ScyllaDB and mostly use your application as it is. I didn't mention it, but ScyllaDB is an open source project. You can look at the code. It's on GitHub. So yeah, if that's your thing, you're welcome to use the open source project, maybe also contribute. We have, a community that's helping. Then we have our enterprise version, and that's for companies that run in production and have mission critical applications running. And with enterprise, users get a few additional features, as well as our 24/7 support. And last but not least, I see there's a problem with the screen sharing. Sorry about that. Let's see if this changes. That's weird. Okay. Yeah, sorry about that. Thanks for letting me know. I'll keep an eye on it. Can you see now the flavors slide? Okay, thanks. Okay, so back to the slide, 3 flavors: open source, enterprise, and last but not least, ScyllaDB Cloud, which is database as a service offering. And with ScyllaDB Cloud, basically, you don't have to worry about administrating the database. You get it as a service, very similar to DynamoDB. And you can focus on developing your application without worrying about backups and repairs, upgrades, performance, security hardening, and so on. You can just focus on your core business, which is probably the application. Okay, for some reason. Okay, I see it is changing. Okay, some comparisons. I don't really want to get into this, but you can find all the details, the specific benchmarks with details for how to recreate them. when we compare to other databases. Let's take this one, Apache Cassandra. So one of our customers replaced 40 Cassandra nodes with 4 Scylla nodes. They got a solution that was 2.5x cheaper, and they got 11 times better latency. So yeah, it makes a lot of sense to switch to ScyllaDB for different reasons. Okay, this is the example that I told you about. It's a quick demo that you can actually run on your own. I will share this link to the demo itself. It shows how to run 1 million operations per second in the cloud on AWS, I believe. And this is the monitoring stack that shows how it's done. And this is something that, yeah, with just a few clicks, you can see on your own. And you can see the latencies and so on. Okay, with that, let me move on to the architecture. So I mentioned the idea of a node. A node is basically the database software running on a machine. Okay, that's a node. A node consists of different shards, and each node in ScyllaDB, again, the same goes for Apache Cassandra and DynamoDB, as well as other databases, contains a portion of the database content. Okay, so in a typical cluster, we have in production between 3 nodes. That would be the minimum, all the way to some users that are running hundreds of nodes together. So they run hundreds of nodes, usually across multiple data centers, and all these nodes work together to form a cluster that is able to serve requests. In ScyllaDB, I mentioned high availability. So all nodes are created equal, okay? All nodes in this slide, you're seeing a 5-node cluster as an example. All nodes are able to serve requests. We don't have a single point of failure, and we don't have a concept of leader, follower, master, slave, or any other name you want to call it. All nodes are created equal. All nodes can serve requests. And the communication between the nodes is done, well, there's inter-node communication. So again, no single point of failure. Great. So I mentioned that data is replicated. Each node holds a portion of our data. And this is done automatically. So as a user, you don't have to worry about that. It's done by the database, but it's important to understand how this works when you're thinking about data model. So an important setting is called the replication factor, sometimes abbreviated as RF. And replication factor is simply the number of nodes where data are replicated. Okay, this is set for the key space. A key space is a container of tables. And here you can see a very simple example of how to create a key space. You simply define the name and you define the replication factor, in this case to be 3. What does it mean if the replication factor is 3? If we go back to our previous cluster with 5 nodes, each piece of data that we write to the cluster is going to be replicated to 3 different nodes. Okay, so let's say this light blue cube is a piece of data. It's replicated to 3 nodes, node 1, node 2, and node 3, and so on. Each data is replicated to 3 different nodes. Okay, if the replication factor was defined as 4, then it would be replicated to 4 nodes. Okay, this is something that's set by the user according to your specific needs. Now, of course, there's a trade-off here, like in so many other things in databases. The higher the replication factor means that the availability is going to be higher, right? Because we're going to have more redundancy. On the other hand, it requires more hardware and can also impact performance. Okay, so how is data replicated across the cluster? So what I'm going to show you now is, again, something that happens under the hood. This is, again, showing you with ScyllaDB, but it's pretty much exactly the same with Apache Cassandra and Amazon DynamoDB. So what happens under the hood when we write data, say a specific row? So I'm looking at an example of a table, and this table has 3 columns: pet chip ID, time, and heart rate. Okay. Each table requires the user to define the partition key. The partition key is an important concept. I'll talk about that a bit more. The partition key can be 1 or more column. So in this example, it was defined just as 1 column, the pet chip ID. And when we write data to the database, what happens under the hood is that the node takes the value of the partition key, pet chip ID in this case. It performs a consistent hash function, also called the partitioner, on this piece of data. And according to the hash, it knows which nodes are responsible for this piece of data. Okay, so partition key is an important concept in data modeling. I will talk about that more later on. Okay, another important concept, the consistency level. So I talked about availability. In NoSQL databases, not all of them, but the subset that I'm talking about, like ScyllaDB, DynamoDB, Cassandra, and some others, availability is given a preference over consistency. Now, that doesn't mean that the data is not consistent. However, we have something called eventual consistency as well as tunable consistency. And that goes back to the question that I got at the beginning of the talk. So ScyllaDB doesn't support ACID transactions. Okay, we do have an option to set the consistency, and this is done using the consistency level. Now, consistency level, or CL, basically means the number of nodes that must acknowledge a read or a write request. This can be set per operation. Some example values are 1, quorum, local quorum, or all. And again, there's a trade-off between the consistency and the availability. Okay, so for example, if I have a query and I set the consistency level to be all, what that means is that all replica nodes, say we have a replication factor of 3, it means all 3 replica nodes must return the value in order for the query to be successful. Okay, so that means the consistency will be higher, but it might impact availability, because if one of our 3 replica nodes is down, say, I don't know, it had a hardware failure, then the query would fail. Okay, so we have a trade-off between consistency and availability, and the consistency level can be set per operation. That means that you might have a write request that, a specific write request that requires a high consistency level, while maybe another write request or a read request requires a lower consistency level. Okay, and that's also important to understand as we're talking about data modeling. I mentioned multiple data centers. So the database is built to be topology aware, and that means that it can run, it's distributed, it runs on multiple nodes, as I've said, and these nodes can also be in different data centers. The database is built to take this topology into account. So for example, we can define that a user, say in this example, we have 3 data centers, a user making a query from the US would be served from the US data center. And that would, of course, improve performance because there is some latency to transfer data between the US and, say, I don't know, China. So one reason is performance. The second is for maybe some compliance or regulation issues. So some countries or jurisdictions require that the data of the users remain in that country or that area. So we can do that by defining multiple data centers. And the third is what I keep talking about, which is availability. And we had examples of, it doesn't happen very often, but it can happen where an entire data center went down. There was a fire. I think it was somewhere in Europe. And there was a big outage, of course, many websites went down, but because our user was using multiple data centers, they were still able to serve requests. So it creates redundancy. I think it was Kiwi.com, which is a travel company. If anyone is interested, I can probably find the details of that case. So there's a question, do we distribute nodes globally or can they be in the same data center? So the answer is yes. Both of them are true. So they can be either in the same data center or they can be distributed globally. It depends on your needs. And even within the data center, the database is also aware of different racks. Okay, so that's another redundancy that data centers typically have. They have different racks. And even if an entire rack goes down, we can have nodes on other racks. Okay. Moving forward, let's dive deeper into the basics of data modeling. Okay, so this slide compares NoSQL data modeling to relational or SQL data modeling. And I use it just because a lot of engineers have a background in relational databases. So typically, in relational databases, when we think about data modeling, we start with our data. We think about the entities, the different relationships between those entities. We create an entity relationship diagram. Then we create our schema. And finally, we think about our application and our queries. This is the typical process. When we think about NoSQL data modeling, there is an important difference here. And instead of thinking about the application at the very end, we have to think about it at the beginning. Okay, so we think about the application and the data at the beginning, and the outcome of that process is our actual model. Okay, and the reason we have to think about our application is we have to think about what are the queries that we're going to be performing, how often are we going to be performing them, and what are the requirements from those queries. For example, what are the consistency requirements? We have to think about things like denormalizing data and so on. Okay, maybe a quick poll question just to make sure people are with me. So what's the most important thing for your project's database? A few options here: low latency, high throughput, strong consistency, availability, cost, or manageability. If you could quickly answer that in the chat window, yeah, just to make sure I'm not talking to myself. So what's the most important thing for your project's database? Is it low latency, high throughput, strong consistency, high availability, the cost, or manageability, or you don't know? So let's take a few seconds so people have a chance to answer in the chat window. So I see manageability, low latency, manageability, high availability, and then cost, reporting, and low latency. And development skills. Okay, Thanks for answering. Okay, so let me move forward and talk about a few more concepts. When I talk about data modeling, I mentioned some of these concepts without really explaining them. So I did say a key space is a container for tables. It can have one or more tables. And a cluster can have one or more key spaces. The important, or maybe most important setting that we set for a key space is the replication factor. As I mentioned, how many copies of data do we have? For each table, we have different settings like the partition key and the clustering key. And within a table, we have rows and columns, just like you would imagine in relational databases. And the way that data is ordered within the table is done according to the partition key. Okay, so we have the partition key, and then we have the data. And if we define a clustering key, which I'll talk about in just a second, then it will be ordered according to the clustering key. Okay, so key space, I already showed this. This is how you would define it, and we're going to see that in the lab that I want to show you in just a bit. This is how I would create a table. Yeah, it's very straightforward. So this table called heart rate V1 has 3 columns. It's actually what we saw before. It's the PET chip ID, it's the time, and the third column is the heart rate. So for each column, we define the type. You can see integer or timestamp or UUID. And very importantly, we define the primary key. Okay, the primary key has 2 parts. They are the partition key and the clustering key. Okay, the partition key has to be defined. It has to be at least 1 column. And the clustering key can be defined, but it's not mandatory. So it can be 0 or more columns. Oh, okay. You're supposed to be seeing the table slide now. I think that's the one you're seeing. Let me know if not. Okay, so I'm happy it's back. So a partition key is not exactly the same thing as a primary key for relational databases. There are some differences. And when we talk about NoSQL, ScyllaDB, as well as Apache Cassandra, we talk about CQL. It sounds like SQL, but it's different. It stands for Cassandra Query Language. You have different DDL or data definition queries, as you would imagine: create, delete, alter, select, insert, update, and so on. However, there are some differences. That's a bit more advanced, but maybe I'll have time to talk about the differences. So to interact with a cluster, we typically use the CQL shell. And to do that, we would write CQLSH and the IP of the node that we would connect to. In real-world applications, we would use drivers, not a CQL shell. Today, I'm going to show you the lab with a CQL shell just because it's easy to demonstrate. So usually the CQL shell is used for testing purposes, for demonstration, yeah, just to see what's going on in your cluster. But for actual applications, we use drivers. Okay, let's dig deeper into partitions and keys. So, okay. I already talked about replication. Don't want to repeat this, and I showed you this slide. Okay, so the example that I'm showing, I'm also going to show you in the lab. So it's a very simple application where we have pets, and each pet has sensors, and these sensors measure different measurements for the pet, say the heart rate, and they write that those measurements, they write them to the database. Okay, so it's a very simple application just for the demo. And here we create another table, heart rate V2. We have the same three columns, pet chip ID, time, and the heart rate. However, this time, the primary key has two parts, pet chip ID, which is the partition key, just like we saw before. But this time, we also define a clustering key. And the clustering key is the time. What does that mean? So this is how the data would look like on the database. We have the pet chip ID right here, and that is the partition key. And for each partition key, we would have the other columns, which are basically pairs of key value pairs, say the time and the value of the time, and the heart rate and the value of the heart rate. However, because we define the clustering key, they would be ordered for a given partition according to the clustering key. So our clustering key was time. So if we have more than one value for the partition key, then the values would be ordered according to the time. Now, why does this matter? It matters because think about a partition that has maybe millions of rows for the same partition. If we have the data ordered according to the clustering key, we can query according to that column and find our data in a very efficient manner. Okay, so this brings me to performance, and I mentioned single millisecond queries, and to do that, it requires very specific data structures. So if you remember when I talked about the way the database finds a specific row, it does that according to the hash function performed on the partition key. So that's very, very fast. It knows immediately which node holds the data. And within that node, once it has the partition, it can find the data according to the clustering key very fast. As a side note, clustering key is the term used in ScyllaDB and Apache Cassandra. However, in Amazon DynamoDB, it's called ordering key. Okay, so it means the same thing. I don't know what's the reason there are different names. Actually, ordering key is probably a better name. But anyway, it's the same thing. Okay. Let's see how much time we have. We're good. And let me go through the hands-on lab. And again, feel free to ask questions if you have them. Okay, so I'm going to be showing you, let me maybe make this font size a bit bigger. Okay, so I'm going to be showing you a hands-on lab. You can see what I'm doing and you can run it yourself later on. So this is a very basic lab showing some of the examples that I talked about. And I start this lab by running this line of code, which I already did, command rather. And what this does, it's Docker, and it simply runs a single node with ScyllaDB specifying the version, and that starts a single node cluster of ScyllaDB. Once I have that up and running, I can execute the node tool status command. And what this does is it checks the status of my cluster. I can see that I have one node in my cluster and that it's up and running. It's ready to serve requests. Now, if you remember, I said that in production, we would run a cluster with at least 3 nodes. Okay, so what I'm doing right now is just for learning. Don't do this in production. Typically, you wouldn't be running using Docker in production, although it's possible. but you definitely would not want to run a single node cluster. You would have at least 3 nodes. Okay, so we can see that our cluster is up and running. It has a single node. To connect to this node, I simply run the name of the node and CQLSH. If you remember, the CQL shell allows me to interact with my node, perform queries, and now I'm ready to do that. And let me move on to create a key space and the table. Okay, so again, I have a single node cluster. I connect to it with a CQL shell, and I'm going to create a key space. If you remember, a key space is a container of tables. I define it with a replication factor of 1. Okay, I get a warning that it's not recommended, but I already told you that this is just for the demo purpose. And now using this key space, I can define a table, and I'm going to define exactly the same table that we saw in the slides, 3 columns, PetChip ID, time, and heart rate. And now we're going to have a key space with a single table and a single partition key, which is the PetChip ID. Okay, now that I have my table, I can insert data. And again, this is very straightforward. I insert data into the table and I provide the values, the PetChip ID, the timestamp, and the heart rate 100. And just like you would expect, I can now read the data that I just wrote. Okay, so I select from the table and I provide the primary key, PetChip ID. Okay, what would happen if I insert more data into my table for the same pet? So I insert into heart rate V1 into the same table. I provide the same PetChip ID, but I provide a different value for the heart rate. What do you think would happen? Would this succeed? Would this fail? Feel free to guess in the chat window. So the question is, what would happen if I insert data into the table with the same partition key? Any idea? If not, you can guess. So one guess is override. Any other ideas? We're inserting data into the table with the same partition key. Denied, which I think means that it would fail. Other guesses or thoughts? You can write in the chat window. What would happen if I insert data with the same partition key? New row, new entry with the same key, update. Some of you are correct, and what would happen is that the data would be overwritten. So we didn't get any error message when I insert it, but when I select, just like I did before, I would see that I only have 1 row and that my insert was actually an upsert, okay? Instead of adding a new row, my previous row was overwritten with the new data. So that's not what I meant to do. And let's understand what we can do in terms of data modeling to overcome this. Okay, so I'm going to answer that, but before that, I want to circle back and talk about the clustering key. Okay, so what happens if we look at the previous table? If you remember, it has 3 columns. So there's a question, do I mean that the entire table has been overwritten? And the answer is no, just the specific row was overwritten. the table had a single row with a single value for the PetChip ID. And when I wrote a different value for the same PetChip ID, which is the partition key, instead of what the user expected, which is to add another row, the first row was overwritten. Okay. So yeah, no problem. I'm going to show how to solve that in just a bit. What would happen for the same table, heart rate V1, if I want to query according to the PetChip ID, which is the partition key, just like before, but also according to the time. So what would happen if I run this query? Any guesses? Would this query succeed? Would it fail? Would something else happen? Again, you can write in the chat window. What happens if I write this query, select from the table, in addition to providing PetChip ID like before, I would also provide the time. Any ideas? So some of you think that it would work. Any other thoughts? Write in the chat window. I will get a number of records. Okay, so, or one. Okay, so let me just run it and try. And I can see that when I run this query, I get an error. Now it looks like an error, but it's actually more of a warning. And the database is basically telling me that it can run this query, but it would be very inefficient. So if I want to override this error, I would have to use something called allow filtering, which basically does a full table scan. Okay, now what's happening here? I mentioned that when we perform a query to the database knows where the data is according to the partition key. It knows on which node the data exists. And within that node, there might be, for a given partition, there might be millions of rows. So if we have the data for a given partition without any order, what the database would have to do is it would have to do basically a full table scan to find the rows that are fitting to my query, so to the time in this case. So that's not very efficient. Again, if you think about big data, it can take a long time. So the database is warning me, be careful, maybe that's not what you meant to do. So how can I overcome that? I'm going to define a new table, call it heart rate V2, and it looks exactly the same, 3 columns, primary key with PetChip ID, but in addition to the partition key, which is the PetChip ID column, we now define the time as the clustering key. And if you remember, see if I have this drawing right here. Yeah, I'll go back to the slides to show you what I mean. So if you remember this slide, we had the partition key, and now because we defined the time as the clustering key, our data is going to be ordered according to the time. Okay, so now we can efficiently query according to the time and not just according to the PetChip ID. Oh, great. So where was I? Okay, so I defined the table, just like I said, and now I'm going to insert some more rows into the table. And I don't know if you can see it, but I'm going to be inserting different values for the same PetChip ID. So for the same PetChip ID, I insert different values. And now running the query that I showed you before, querying according to the partition key, PetChip ID, and the clustering key time, I can see that now the query would work. and it runs very efficiently. Okay, so it knows exactly where the data is. And not only can I query according to the clustering key, but now we also overcame the previous problem that we saw where data was overwritten. So now for a given partition key, we can have more than one heart rate and time value. Okay, so we're seeing here single pet chip ID, and we have multiple values for the time and for the heart rate. Okay, so the data is not overwritten. And we can see this more specifically if we read all the data just for this given pet chip ID. Okay. Let me show you a few more examples. So I mentioned that we can define a table with more than one column for the partition key or the clustering key. So in this example, we define a new table, call it heart rate V3. And this time we have the pet chip ID, the time, and the heart rate columns, just like before. But we add an additional column, call it pet name. And our primary key this time has 3 columns. 2 of these columns, you can see in the parenthesis, are pet chip ID and time. And these columns would be the partition key. Pet name would now be the clustering key. Okay, a few rules about the partition key. I mentioned that each table has to have a partition key with at least 1 column. And if we define a partition key, all the different columns have to be provided in the query. Okay, so let's insert some data. I insert one row. And if I try to run this query, I'm running a query that's reading the data, but providing only the pet chip ID column. I get the same warning or error as before. So I'm trying to read data from a table that has 2 columns in the partition key, but I provide just 1 column. So let me go back to the slides and explain how it looks like on the actual table. Okay, so if you remember, we write data or read data, doesn't matter, we query the database. And the database, in order for it to know where the data resides, it needs to perform the hash function on the partition key. So in this example, the partition key is pet chip ID. But in the example that I showed you, it's pet chip ID plus another column, doesn't matter which. And the database takes both of the columns in the partition key, performs the hash function, and then it knows which node has that data. Now, if we only provide one of the columns for the partition key, then the database has no way to perform the hash function, and it doesn't know where the data is. Now, that maybe it doesn't sound so bad in these small examples. And actually, if I added allow filtering and I run it, it would take less than a second. But this is because we have a 1 node database with 1 row, something like that. Imagine, I don't know, terabytes or petabytes of data running on hundreds of nodes, then running a full table scan, not knowing where our data is, can have implications, of course, in terms of performance, but also load on the database. It doesn't mean that you shouldn't do it. Maybe there are special cases where it would make sense to do a full table scan, but you should be aware of what you're doing and know that it has its trade-off and implications. So let's try this again. And this time I'm going to provide the pet chip ID. I'm going to query again, provide the pet chip ID and the time, which is also a part of the partition key, if you remember, and the pet name, which is the clustering key. So if I run this, the query works, and it works very efficiently. By the way, the clustering key doesn't need to be provided. Okay, the clustering key doesn't need to be provided. It can be provided, but it's not mandatory. Okay, as opposed to the partition key, which is mandatory. Let's look at another example. So heart rate V4, same 4 columns, but now the only difference is that our primary key is different. We have pet chip ID as the partition key, and pet name and heart rate are going to be the clustering key. What does this mean? It means that data is going to be ordered just like before according to the partition key, but within that given partition for a given pet chip ID, if we have more than one value, it's going to be ordered according to the pet name. And if we have the same pet name, it's going to be ordered according to the heart rate. Okay, and now I can query according to pet name and heart rate as well. Okay, and if I insert some data and read it, then it's going to work. Take my word for it. And you can also run it yourself later on. Like I said, I'm going to share the link to the lab. But we're almost out of time, and I want to cover a few more things. So let me move forward. That's not what I wanted to do. Okay, so choosing a partition key. This takes me back to data modeling. Choosing a partition key, as you just saw, is really important when you create your data model. It has an impact on the performance, on data distribution and replication in the database. So yeah, it's an important decision for choosing a partition key. Some things you would want to achieve when you choose a partition key. You want to achieve high cardinality and even distribution. And of course, the opposite of that is you want to avoid low cardinality. What does that actually mean? Maybe an example. So let's say our table is people in the United States. So if I choose the state as a partition key, then that's probably not a good choice because we have just 50 states in the United States. So that's low cardinality. That would not be a good choice. Not only that, but our distribution of people would probably not be even because we have some big states with many people like California, and we have small states like, I don't know, maybe Delaware that has comparatively small number of people. So the data would not be distributed. And some of our nodes, the ones, say, with the partition key of California, would have way, way more data than the ones from Delaware. So that's one example. Some related things are hot partitions and large partitions. So the example I gave of California would be a large partition. And that means that we're not making the best utilization of our hardware because some nodes are highly loaded while others are hardly have any data at all. Another thing we have to think about is hot partitions. So hot partitions are a bit different. Hot partitions are partitions that are queried more often than others. So say in our application, for some reason, people in California are queried more often than people in another state. Okay, so then that would create a hot partition, and the nodes that have the data for California would be overloaded as compared to others. Let's skip this because we're almost out of time. So some examples of generally good partition keys: user ID, username, sensor ID and time, and so on. Not so great partition keys, like I said, state, age, the favorite NBA team. I don't really follow NBA, but there aren't that many teams, probably a few dozens, so that's not a great choice. About the clustering key, like I said, it allows us to query according to the clustering key, and we can use ranges. So for example, for the time, like you saw, we can say between this time, and that's very useful. Another thing is that it allows us to use limit. So say we want to query, we have a typical query that's the last 3 heart rate writes. So we can order it according to the heart rate order, and then we can just pick the last 3 using the limit keyword, and that would be a very efficient query. Let's look at the time. So we don't really have time to talk about drivers. There's an entire course on ScyllaDB University about drivers. We have drivers in different languages, C++, Java, Node.js, and some others. You can have a look and see examples for how to use them. Java, Go, and so on. Yeah. Yeah, I won't go into ScyllaDB specific drivers. Yeah, maybe a few more words about advanced data modeling. So for each one of these topics, I can probably talk an hour about each topic, but just so you're aware of them, and if you want to learn more, you know that they exist. So denormalizing data in NoSQL databases is done differently. There's also a lesson about this on to perform transactions. So it's not completely ACID transactions, but it does provide it or have your data automatically erased after a certain time period, say after a week. Say in the heart rate example, we write the dog's heart rate every second, but we want to keep it just for a week, so we can define that, and the database would automatically delete it. Counters are a special column that allow us to, just like you would expect, raise the counter in a consistent manner. And user-defined types are a special type that's more advanced. And you can see all these examples in ScyllaDB University. We have a community forum where some of our engineers hang out there, but also community members ask questions, share their use cases, and so on. So that's at forum.scylladb.com. And our database as a service, ScyllaDB Cloud. By the way, you can start a trial cluster there. Just a few clicks and you have a cluster up and running. You don't need to provide credit cards or anything like that. It's very straightforward. And you can run the examples that I showed on ScyllaDB Cloud. Yeah, with that, let's wrap it up. Feel free to reach out. Like I said, I'm going to send you an email tomorrow, probably, with the slides, with the lab, with some links. And yeah, thanks for attending. Feel free to reach out. My email is guy@scylladb.com. And yeah, hope you enjoyed it and learned something. Thanks, everyone.